Okay, thank you very much for organizing this program and for the invitation. It's really a pleasure. After this COVID time, it's really a pleasure to see so many friends and collaborators together. And yeah, also it's a great pleasure to celebrate Professor Dani and his research. So I'll be talking about joint work. So this will be a joint work with Jialong Li and Kagri or Char, how you say it, Turkish, I was told. So yeah, is it big enough so people in the back can still see it? Okay, so the basic problem which I will discuss is the following. So we fix mu, which is a probability measure on SLN-R, and we normally assume that this measure has this integrability condition. So this integral is finite, so run the arguments. And then we also have X, which is a homogeneous space of G. And so then we have a natural action of G on the space. So the orbits are typically very complicated. And so a natural way to understand this action is to study the stationary measures. Yeah, so a measure, so nu, which is also a probability measure on X, is called mu stationary. If convolution mu with nu is equal to nu. So this is the stationarity conditions. And so the aim of this talk is to discuss some of the old and new results about classifications of ergodic stationary measures. So classify ergodic stationary measures. Okay, so first let me recall some of the well-known results, but somehow those are actually quite important results in homogeneous dynamics. So there are several classes of these questions which have been extensively studied, and so the first, at least historically, I guess, the first class of examples is actions on projective or it's also called flag manifolds. So X is a flag manifold. So namely, X is equal to G factor Q. Q is going to be a parabolic subgroup. Subgroup in G. So for instance, action of G on the projective space. So that's an example you want to think about. And so here there is a theorem which started with the work of Furstenberg. And then there are refinements by Guivarch G and by Benoit and k. So and so what? Under quite broad conditions, it turns out that one can give a complete classifications of stationary measures. So suppose suppose that okay, so one group which will play important role in my discussion is the group which is obtained by taking the group generated by the support of mu. So this is a subgroup of G. But then somehow it's not so important what this group is, but it's important what the risky closure of this group is. So so H is going to be the risky closure of this group. So it's an algebraic subgroup of SLN, and so it turns out that depending how this algebraic subgroup looks, so the answers will be different. And so here we suppose that H, so the risky closure is semi-simple. Then what is known that there is a one-to-one correspondence between stationary measures and compact orbits of H in X. So there is a one-to-one correspondence between ergodic stationary measures and compact H orbits. Compact H orbits in X. So ergodic stationary measures in X and compact H orbits in X. So namely, if you have a compact H orbits, just by usual compactness arguments, there exists a stationary measure, but it turns out that the stationary measure is unique, and somehow this construction gives us the bijection. Yeah. So so the second class of examples which has been extensively studied is finite volume spaces. Volume spaces. So namely, X is going to be G factor lambda, where lambda is a lattice, lattice in G. Okay, and so here there are two subclasses. So the first, at least historically, first case is when H is one parameter unipotent subgroup. Unipotent subgroup. So so this has led to the theory of unipotent flows, and but so interestingly, if one looks how this theory was starting, so it was in part motivated by the Oppenheim conjecture in number theory, and Raghunathan observed that somehow having progress about understanding such orbits of H could be helpful in solving solving Oppenheim conjecture in a number theory, and then Dani took a measure theoretic look on this problem, and so so he formulated So I even checked, it was in 81, in the paper in 81, he formulated the following general conjecture. So yeah, I already made myself embarrassed. I think some time ago I was giving a talk in Tata, and I was quoting Dani's theorem, and then it turned out to be theorem of Mrs. Dani. But so this time I checked carefully. So okay, so yeah, so what this conjecture says is that all H invariant ergodic measures are homogeneous. So so here, because H is a billion, every stationary measure is also invariant. So one can just study invariant measures. And so what is homogeneous? So maybe I should also explain that. So it means that nu is L invariant measure on say L G lambda, where this orbit supports finite invariant measures. So namely, I have to assume that L intersection G lambda G inverse lattice in L. Yeah. So yeah, I think it's fair to say that Dani was the first which realized the importance of this measure theoretic approach to study unipotent flows, and this in the end turned out to be the key of proving even topological results about orbit closures. And so eventually, oh yeah, by the way, already in this 81 paper, there were some special cases, special important cases of this conjecture, which were proven. And so in early 90s, roughly, this conjecture was proved by Ratner in full generality, proved by Ratner. So, and then the second subclass, which comes from the works of Benoit and Kerr. So, and I mean, there are also related conjectures of Furstenberg about this. So, so H is semi-simple. So, namely, this is the risky closure. Right, semi-simple and no compact factors. So so then again in the setting, important theorem of Benoit and Kerr says that all stationary measures, stationary ergodic measures are homogeneous. Yeah. So so this is the case where the risky closure is semi-simple, and then so one can try to move on from these two basic cases and consider a hybrid situation. And so so here is a hybrid example which was studied by Sargent and Uri Shapira. Hybrid example. And it's kind of nice to have this concrete example in mind, because so the general case would have a very similar picture. So, but it's very nice to visualize what happens. So here X is going to be rank 2 discrete subgroups. Subgroups in R3. So this is not a finite measure space anymore. But what we can notice that every rank 2 subgroup defines a two-dimensional subspace. So there is a natural factor map going into Grassmannian of two-dimensional planes in R3. So this is planes. Space of planes in R3, right? And this is so this factor space fits into the first class of examples. So we can identify it with G factor Q, where Q is a maximal parabolic subgroup in G, and then the fibers. So the fibers of this bundles of this bundle are going to be again homogeneous spaces. So they are of the form R factor R factor. So maybe I should have my notation sorry, no, Q factor R. So Q factor R. Where but the fibers have finite measure and isomorphic to P GL2R factor P GL2Z. So it's really a marriage of the first two examples, which we have seen before, and so in this setting. Sargent and Shapira obtained classifications of the stationary measures. So all ergodic stationary measures are, and so the first example is kind of natural to guess if you start thinking about the space. So the point is that on the base space there is a unique stationary measure coming from Furstenberg and yeah, from this already in Furstenberg case, right? And so then you just have to somehow define the measure compatibly on the fibers. And so so the first situation is the measure nu, which is integral over G factor Q. And here I push measure lambda, certain measure lambda by G, and then I integrate over measure nu bar on the base. So where so here the notations are, so nu bar is going to be the stationary measure on G factor Q, which we know is unique, and so lambda is going to be the invariant measure on this fiber Q factor. So it's PGL2 invariant measure on the fiber, and so if we integrate this measure, then we obtain the measure on the whole space, which has nice properties. So somehow I want maybe to draw a picture. So so here we have the base, which is G factor Q, and the base is going to support a unique stationary measure. And then on the fibers, so somehow we first we can put the obvious measure, but remarkably it also turns out, so one thing which they discovered is there is also other family of example which do exist, and so namely the other family of stationary measures, which okay, it doesn't exist always, but in some situations. So here I would write maybe delta of I y, again d nu bar y, where I is going to be a map from the base to x, which is gamma. Sorry, not to x, to finite subsets. Subsets of x, so it's you can view it like as a multi-valued function, which is gamma, which is so how do I say it? It's support mu equivariant section of the factor map, so which I normally denote as pi. So we have this factor map, and then we have gamma equivariant section of this factor map. So namely, we could have like a graph of some multi-valued function, which and then the delta is going to be just a combination of Dirac measures on the fibers, right? So, but somehow if you have such a graph, then of course you also do get these stationary measures coming from the graph. So it's kind of quite surprising that such equivariant sections exist in many cases, but indeed, so this is what happens, and so they get a complete classification of stationary measures for this situation. So now I'm moving on to yeah. So so I is going to be a map going from the base from G factor Q to finite subsets upstairs, and so basically if I have a point here in the base, so then there would be a so I can assign to it finitely many points. Well, I don't know, maybe like these 3 points, and then I can do it in an equivariant way, so that it respects the action by points in the support of gamma. And so if you and then if you do it okay, if you have such a map, one can just put a measure on the graph of this map, where we take a new bar and push it forward to the graph. So there is this natural measure coming from just usually if you have a graph of function, you can put a measure on the graph, and if it's equivariant, then yeah, so it's still yeah. Yes, and so this is indeed a complete classification in the setting. Yeah. So so now somehow it's a quite mysterious situation, and it still remains quite mysterious. But at least we tried to explore what can happen. And so So those would be the notation for our talk. So G is as before SLN-R. Right inside G, there is we fix some parabolic subgroup, and R is going to be a subgroup of G, and R naught is going to be algebraic subgroup of R, and we additionally assume that R naught is normal in sorry, this is of G, but I guess I also want to so it should be of Q, and so R naught is going to be algebraic and normal in Q, and so and then we also assume so we assume that if I take the factor space Q factor R naught, so this space is semi-simple, no compact factors. Then so inside here I would have lambda, which is R factor R naught, and so we are assuming that this is a lattice in S, and also we have this group H, which is the risky closure of the group generated by support of mu, and so we are assuming that H is so H is going to be SL2R. Well, in fact, maybe now once I talk about it, I didn't really specify anything about H in this situation. So, but somehow, okay. So, so those results are in particular for the case when H embedded. So H is a copy of SL2. SL2R in SL3, which is irreducible, or actually P okay, SL2R. So this is irreducible embedding of SL2R in SL3. So irreducible embedding. Yeah. So I forgot to mention that. Okay. So okay. So now if we have this data, then we also can build a bundle in a similar way to this picture. So namely, we have a homogeneous space X, which is G factor R, and so because R is a subgroup of Q, there is a natural factor map to Y, which is G factor Q. Yeah. Embedded in SL3, and this is irreducible embedding of SL2 in SL3. Yes, yeah. So you have this up to conjugation, essentially unique embedding, right? So okay, so so we have this natural bundle, and so of course, in order to classify stationary measures here, first we need to know what the stationary measure here R, and this is known from the theorem of Benoit and Kevich, the first theorem in this talk, right? So then the stationary measure are coming exactly from compact H orbits. So we fix say y0, which is say H y0. So this would be compact H orbit, and we know that y0 supports unique stationary measure nu bar. Right, so then in the base here there will be a stationary measure nu bar, and also this y0 we can write as H factor Q0. So Q0 is simply a stabilizer of y0, and choosing Q conveniently up to, so we can basically up to conjugation we can assume up to conjugation we can assume that Q0 is exactly H intersection Q. Yeah, so Q is a stabilizer of identity cassette here. So if y0 were identity cassettes, then that's what we get. Right, so if I have this picture, then I can consider the pre-image. So this would be X0, which is just a pre-image of y0. And so another important bit to keep in mind that the fibers of this bundle are Q factor R, which are S isomorphic to S factor lambda, and so the fibers are finite volume homogeneous spaces, and in the base we have flag manifold. Okay, so and maybe another remark it's natural to make here. So so Q or the stabilizer of a point naturally acts on the fibers of the bundle. And so and for us, actually, it would be crucial to understand how this action actually looks. So so we also denote by phi. So this is the natural gamomorphism going from Q0 to Q factor R0, which is S. So somehow, so each fiber, so on each fiber, the stabilizer of this point would act, and so this is so the phi describes, and yeah, of course, because it's a homogeneous, all these actions look kind of the same. So okay, so so now okay, so what can we say in this situation? And so actually somehow the answer is different depending on how what Q0 is and what this map phi is. So somehow it's not so clear how to formulate things completely uniformly, but one can go and discuss several cases. So the first, so this is kind of by now classical case. So this is when Q0 is equal to H. So namely, this would mean that y0 is just a point, and then we have Dirac measure. So we have a point which is fixed by H. So then the stationary measure on the base is just the Dirac measure. boring, but then in the fibers we have this finite measure spaces, right? So this is basically the same as saying that the measure in the base is simply the Dirac measure, but this is just the finite volume situation, and namely, so this is Benoit case. Okay, so so then what is the other option? So this has to be a compact orbit. So so we can actually say what the stabilizer of Y naught is. So the second situation would be when Q naught is parabolic. Parabolic in H, and but this is also kind of a boring case. So it could happen that the action, this action phi on the fibers is trivial. So so namely, kernel of phi is equal to Q naught. So so then nothing really happens on the fibers, and so but there is still it's not like completely immediate, but so that's an easy case of the situation which could happen. So so in this case, one shows that all ergodic stationary measures which project to the measure on to this measure nu bar on the base. So all these measures are described by just integrating Dirac measures. So nu is going to be integration over G factor Q, H star delta X, D nu bar H, where X is a Dirac measure, so is a point in the fiber. Okay, so basically, again, thinking in terms of this example, we can pick a point in the fiber and move it around. So that's also kind of similar to this case, but easier somehow. Okay, and then so the third case is a generalization of the hybrid example. So so the third situation. So so here again, Q naught is parabolic in H, but the kernel of phi is finite. So here we have a quite rich action on the fiber. So here we have a theorem, at least in the irreducible situation. So assume that action of H on Rn is irreducible. So then we can classify then all ergodic stationary nu with the property that they project to nu bar are yeah. So yeah. So basically, what I stated on the left-hand side. So this also holds in this setting. So so namely, there are two different types of examples. So first new could be integration over h factor q naught h star lambda d nu bar h, where lambda is the invariant measure on the fiber. So this is the invariant Haar measure, the invariant measure on pi inverse y naught. So so on each fiber, so now I have to go to the picture, I have to go quite far. So okay, let's go. So on one fiber, I put invariant measure living on homogeneous space S factor lambda, and then I move it around by h and average with respect to a nu bar. So this gives us first most natural family of examples, and the second examples are again coming from this graph maps. So namely, I would have integration over again d nu bar, but here I would integrate along the graph. So namely, I is going to be a map from h factor q naught to finite subsets of x. So and this map is support new equivariant section of pi, where pi is yeah. So I denoted it here. So pi is this. So namely, we have a graph of this map I, and we push forward a new bar on the graph, and this also gives the measures. And so in this case, we have a generalization of Sargent-Shapira, and but in fact, so they also proved maybe something very similar or something along this line. So there is also result by Bader, Sargent, and Shapira. In this direction, so finally, there is also another interesting possibility where about what kernel of phi could be. So remember, Q naught is a parabolic. Q naught is a parabolic in H. H is SL2. So there is well, there are not that many normal subgroups in upper triangular matrices, right? So somehow one case which still remains to be considered is the case where the kernel of H is the unipotent subgroup in in this parabolic. So this is essentially the remaining case. So okay, so so finally the fourth case, just to exhaust all the possibilities. So again, Q naught is here. I would even write. So this is group like this, right? A parabolic. Parabolic in H, and we are also assuming that kernel of phi, okay, say maybe up to some finite index, so connected component of the kernel is going to be the group of unipotent matrices. So in this case, we do have non-trivial action on the fiber, but this action comes from the diagonal matrices in Q0. And so, so then, if you look on the phi Q0, so again, up to connected component, this would be some diagonalizable subgroup of one parameter diagonalizable subgroup of S. One parameter diagonalizable subgroup of S. And so, so the action on the fiber is non-trivial, but we don't get any unipotent action in the fiber. So, so that actually makes people worry normally, right? If it's only one parameter diagonalizable subgroup. So in this case, there is no rigidity that one can expect. There is a whole zoo of invariant measures, invariant sets, and so on. So, but still, one can get a classification result in this setting modulo what I just said. So, so in this case, we get that all ergodic stationary measures with pi star nu equals to nu bar. So, so all such measures are given by the following construction. So, so again, I can pick some measure rho living on the fiber over y0, and then I can propagate it, integrate it using nu bar. So, and maybe I also use notation nu sub rho. So, and what is rho? So nu is rho is the measure on the fiber, and so rho is going to be any ergodic d invariant measure on pi inverse y0, which is identified with S lambda. So we have this finite volume homogeneous space, and on this homogeneous space we have one parameter diagonalizable group acting. And if I pick any such measure and integrate, I do get a stationary measure. But what turns out to be the case that we so those examples are the only examples that that one can get. So so here we see, even so we act with a group whose the risky closure is SL2, but one cannot expect somehow complete rigidity result as in Benoit-Kess theorem. There are many exotic measures, but on the other hand, so one can maybe characterize this property as relative stiffness of the action. So, so at least somehow, so the stationary measure are coming from invariant measure living on the fibers. So, yeah. Yes, exactly. Yeah. So in particular, there are uncountably many different ergodic stationary measures. Yeah. Yeah.
So far the
yeah.
No, it was each fiber.
Yeah. So from fiber wise, yeah. Yeah, yeah. So in the base, yeah, the measure could be still bad, but it's kind of unique canonical measure. So it's still kind of a nice. Fürstenberg measure is kind of a nice measure. But here somehow there is also yeah. So in the fibers you can have complicated pictures in the fibers, and right. So the second natural thing one should ask, what about equidistributions? Equidistribution of so once you have a classification of the measure, yeah, so that's what Professor Dani would ask next, I think. So that's what we try to answer as well. So what about equidistribution of yeah, so the second complementary theorem is about equidistribution, and so namely, but here we need to put somewhat stronger assumptions. So we assume that, for example, integral of norm G d mu G is finite. So and then there are two. There are actually kind of two cases which could happen. So somehow first let me start with a strange case. So we have image of H. So image of phi. Image of phi is going to be this up to finite index diagonalizable subgroup. So, but say if the image of phi is not connected, so it's maybe D, disjoint union D D not connected, and also the support of mu preserves a cone in R2. So that's a kind of a bit odd situation, because if we look for action on projective space, there is a unique stationary measure, but if you look on the corresponding action on the set of rays on the circle instead of projective space, it turns out that there are actually somehow the stationary measure is not unique, but one can still describe it. So this is due to Gevarsh and Razi. So there is, and this is kind of also important in our work. What are the stationary measure acting on S1? Okay, and okay. So, but in the setting, what we are saying, what we show, then for every y in the fiber. So now you pick a point in the fiber, and we want to see, or maybe it's better to call it X because it's in the big space, not inside Y. So for every X in the fiber, now we apply a random walk to this X, and we want to ask where this random walk converges. So we consider the following averages. Yeah, we only work this out in situation 4, but I think you also have equidistribution in situation 3, so we somehow didn't go into equidistribution questions. So we started just thinking about 4, but I think you do have, right, equidistribution in situation 3. But somehow the techniques are okay. It really depends what you have to control in the fibers. So here we have the diagonal bit, and in the other setting it's unipotent bit which one has to control. Okay, so we apply a random walk for this, and so all the limit points of this random walk would be those stationary measure. yeah, in general, it doesn't have to converge to anything, but say it converges to one of those standard stationary measures. So how can we characterize this property? So it turns out that this happens if and only if the corresponding orbits of the geodesic flow converge. So namely, if and only if we consider the following classical averages. So here I integrate delta d t x plus delta d t d naught x dt. So and it turns out that this property is equivalent to the property that this thing converges to rho. So namely, if the classical ergodic averages for the sum of these two orbits converge to rho, so this is equivalent to saying that these averages converge to the corresponding measure nu rho. Yeah, and so that's a kind of a bit of an odd situation. And here, this equidistribution phenomena somehow does not is not described by the risky closure, but it's really one has to check what this image of phi is. And how actually okay, so that's described, but somehow how the support of mu looks. So that is not described, and and otherwise we have again that so this property holds if and only if the average 1 over t dt. So that's maybe something that one would expect originally. What is the criterion? But there are also these odd situations where one has to be more careful with describing what happens. So maybe let's see. So what should I do? So maybe just for the last 2 minutes, maybe I try to explain maybe one idea about the proof. So yeah, so somehow what one can do is to define a certain limiting measure. So say we start with nu, which is a mu stationary. Mu stationary, and then for almost every sequence B, which is kind of convenient to index by negative indices. So this is in h to the power minus n. So for almost every such a sequence, if I consider, if I apply this sequence to nu, so the sequence, the sequence of measure would converge to some measure nu b. So this is just a Martingale convergence theorem. And so then it's kind of natural to attempt describing these limit measures first, and then so if we have our space x naught, so we can measurably we can trivialize it. So measurably, it looks really like a product, and then the action on this product space will be given by a certain cocycle. So if we have now h applied to y f, so in the base it's just the usual action. and here it would be certain cycle, which one can also describe quite explicitly what it is. And so if we use this trivialization, then the measures nu b are going to somehow can be kind of written as a combination of measures here and measure here. But in fact, for the action on the base, those measures are just Dirac measures. So that's a kind of useful thing to have. And so these measures will be written as Dirac measure on the base times some mysterious measure on living on this fiber. So we have this type of picture, and so and moreover, those mysterious measures on the fibers have convenient equivariance property. So namely, if we have sigma b, so if we add extra group element, so then we have alpha A0 psi b sigma b. So there is this equivariance properties for those measures, which turns out to be the key to solving the problem. And so what one yeah, unfortunately I didn't have time to say what I planned to say, but at least I can wave my hands. So we have this family of measures which somehow, but they live on different fibers. So it's really not a single measure, but it's like a collection of measures. And they also have this equivariance property that. And then if you somehow start picking different sequences and try to pass to limits and see what you get in the limit. So so then in the limit, you basically, so the upshot of this game with these equivariance properties is the claim that for almost every b, sigma b is d invariant. So that's what one wants to prove in the end. But this is arranged by carefully picking the things. Okay, maybe on some big scale, it's maybe kind of okay, the mechanism is different. How do we control the things? Because we don't have polynomial divergence as in unipotent flows, but somehow one has to develop technology to control products over those cocycles and make sure that they converge to something and construct sufficiently many limits, and eventually somehow yeah, so if I have to summarize the proof in 2 words, it would be establishing additional invariance. Okay, not 2 words, but close to being 2 words. Yeah, additional invariance. Yeah, so additional invariance of those measures. Okay, so yeah, so I'm already over time, so I'm going to stop here now.
Any questions?
Yeah. Mm. Mm-hmm.
In the simplest case of SL3,
mm-hmm.
and maybe so H would be like the top left corner of SL2, right?
Yeah. So I think you have to. So H will be something like this, right?
Okay.
Or okay, maybe it depends how you write it, but and then like
then
if
you have a circle of planes, right? Circle of planes that is in
so the parabolic would be so I guess Q would be something like this. right? But then, so for this situation, you still have this diagonal action on. So like the diagonal part in PGL2 survives, right? So that's it's kind of not irreducible. So this is what happens when H action on R3 is not irreducible. So somehow in your theorem, right, you had that H. Yeah, so it was actually important condition which I forgot, that H acts irreducibly on R3. But if it doesn't act irreducibly, then you have also.
So in this example that you just wrote, if I get it correctly, the circle of planes in which define the support of your measure is the planes that contain the first axis.
Yeah,
invariant under H.
Mm-hmm.
So my question is this measure? So can I find a non-manifold age invariant subset rather than a stationary measure for only for the Zariski dense subgroup?
Okay. So if you so to find the
if I would ask just a topological question, not a measure theory question. So is your fractal invariant measure actually invariant under full age, or?
One construct. Okay, so we have H. Yeah, I guess you can start with a fractal on the fiber, which is invariant under geodesic flow, and then I guess you can just transport it around by H, right? So this okay in the base, yeah, in the base I guess you can even yeah, so I guess you can just yeah, because somehow it's H invariant in the fiber, it's H invariant, so you kind of yeah, transport it and get something in the whole bundle. Yeah, I think that's.
It seems to be this way, right?
Yeah.
So there, it's some, I don't know, it's a phenomena to. I find it weird that. There is some rigidity here, even though you're presenting it as if it's kind of a fractal thing.
Yeah.
Still age invariant, and not.
Yeah.
It's not a manifold.
Yeah. To some extent, right, okay. There is the whole zoo of measures, but it's still a rigidity result. Yeah. So somehow modulo zoo of measures on the fibers. Somehow those are the only measures which exist. Yeah, that's an interesting question. Yeah. In fact, yeah, we can also ask about stationary Radon measures. Yeah, in particular, yeah, if the space is not finite dimension, finite measure space, so FLAC. But yeah, it's yeah, somehow we haven't thought about it, but indeed it would be also very interesting to analyze radon, stationary Radon measures. Yeah.
Any more questions?
Related to the factor Y that you took up, you removed something from here, the middle one, this part, right?
Yeah.
So you took a factor Y and you said that Y contains a compact H orbit. Now, what happens to the situation when your Y is just a disjoint union of compact H orbits, or such a situation never happens?
Yeah, so the dimension wise, right? So we have this big space, G factor Q, this big flag manifold, and then H was just SL2 sitting inside. So then yeah, somehow, so it cannot act. And the dimension wise, you cannot be that this big space is a finite union. but yeah, it's kind of related to Francois' question. So there could be maybe some stationary measure which kind of live on the part where on non-compact H orbits. So it would be kind of nice to see what those stationary Radon measures are, and yeah, I think even like in the base in this flak situation, I'm not sure. Yeah, it seems like an interesting question. Yeah.
Anything else? If not, let's thank Professor Gorodnik once again.